Hi, you guys. We are working through section 11.4, which is all about phase changes. So we have been talking about enthalpy calculations, and we learned that in a constant pressure system, enthalpy and the heat, the Q value, are the same. So we're going to apply this to phase changes. So we already know that in order to cause a phase to change, we have to add energy to the system. And we're adding energy as heat when we're doing phase changes. So there are a couple of different energies associated with changes of state. So the first one is heat of fusion. This is the energy required to change a solid at its melting point. That's the red on the graph, and we can see that that's a pretty small value. So it doesn't take a ton of energy to get something to melt. The next is heat of vaporization, and that is to get it to change from a liquid to a gas. And we know that liquids and gases are much different, much more different than liquids and solids. And so this is a much larger value. That's the blue value, looking at a couple of common molecules. And then the last one is heat of sublimation. So this is defined as going from a solid directly to a gas, which requires a huge input of energy to kind of skip that liquid phase. Okay, so as with everything, we can calculate these values. Now we have been looking at calculating the Q value from a change in temperature, that Q equals mc delta T. Now, you may remember from ninth grade that when you are looking at a graph of water or any substance going from a solid all the way to a gas, that the temperature doesn't rise at a constant rate. So the temperature rises until melting starts. So that's that A to B segment. Then, once ice starts to melt, there's no change in temperature. That temperature or that heat that we're adding is going to changing the movement of the molecules, pulling them farther apart from each other and turning them into a liquid. As soon as all of the solid is gone and we're left with liquid water, then the temperature is going to start to rise again pretty rapidly, and that's from C to D. As soon as we hit that boiling point, that 100 degrees Celsius for water, and we start turning into a gas, that liquid can't get any warmer. And so the temperature is not going to go up until all of those water molecules have been vaporized and are now as steam. And then steam can get really, really hot. So our temperature is going to continue to go up. So what that means is that we will not be able to use our Q equals mc delta T for those flat spots, those phase change spots. Those are actually given values. So we are going to do some calculations, and we're going to need all of this information. So go ahead and box in this page or highlight this. We're going to need a few specific heats because we said that specific heat depends on the state that we're in. So if we're looking at a change of water from ice, solid, all the way to vapor as a gas, we're going to need to use 3 different specific heat values. So we'll need it for a solid, liquid, and gas. And then the delta H fusion and delta H vaporization, these are given values. These are standard values for water. And so we can use those for those flat sections where we won't be able to calculate it. Otherwise, we're going to use the assumption that the heat is equal to the change in enthalpy because this is a constant pressure system, and we'll be able to use our equation of Q equals mc delta T. So let's go ahead and do it. So we want to calculate the enthalpy change for segment A to B on that heating curve. So we're continuing to look back to the curve a couple slides before. So the first thing we need to understand is that the enthalpy that we're looking for is equal to the heat. So really we're calculating the heat, which is related to the mass times that specific heat times our change in temperature. So we need to define our variables. We are going to assume that we have 1 mole of substance, but our mass needs to be in grams. So we're going to use the molar mass to calculate. So we've got 18.016 grams of water. From segment A to B, we are actually as a solid. So 0 degrees Celsius is our melting point. So the specific heat value that we want to use for this is 2.04 joules per gram degree Celsius. And then to find a change in temperature, for this segment of the graph, our initial temperature is -25. Our final temperature is 0, which gives us a change in temperature of 25 degrees Celsius. Once we have all these values, we can go ahead and just plug them in. That's the blue at the top. And we have a heat value of 914 joules. And this is going to be per mole of water. Okay, so that's segment A to B. Now we're up to the freezing point. The enthalpy of fusion is going to be that next flat part of the graph. So the next thing that we can calculate is from C to D. So C to D is the middle part of the graph where we're just at a liquid. The heat is rising, or the temperature is rising as we add heat. So we're going to use the same equation. We're going to assume that the enthalpy is equal to the heat, and heat is equal to mass times specific heat times change in temperature. We're still dealing with 1 mole of water, so we need to convert to grams to use in our equation, same as before. But now we're in the liquid segment of our graph, and so our specific heat value that we want to use is that 4.18 joules per gram degree Celsius. Finally, our change in temperature, we're going from 0 to 100 degrees Celsius. So that gives us a change in temperature of 100 degrees. Once we plug all of our values in, we get an energy change of 7,520 joules. This makes sense that it's much larger because this is spanning 100 degrees versus our last one, which only spanned 25 degrees. We also have a higher specific heat because it's a liquid versus a solid. Okay, so the last segment that we can calculate is E to F on the heating curve. So D to E is going to be our heat of vaporization, which was one of our given values. So E to F on the heating curve, again, enthalpy is equal to heat, and the heat is equal to the mass times specific heat times change in temperature. We're continuing to do these calculations with 1 mole, and so we've got 18.016 grams for our mass. Now we are in a gas, so E to F is above 100 degrees Celsius, the vaporization point, or the boiling point. And so we need to use the specific heat for water as a gas. Our initial temperature is 100, final temperature is 125. So our change in temperature is 25 degrees Celsius. Again, plug in our values, we're going to get 830 joules. Again, it's a much smaller value because it's a smaller energy, or a smaller change in temperature. Okay, so finally we can put it all together. We're going to calculate the total enthalpy change upon converting 1 mole of ice at negative 25 degrees Celsius to steam at 125 degrees Celsius under a constant pressure. So remember that constant pressure system means we can assume the heat is equal to the change in enthalpy. So we are going to calculate the whole change in this system by adding each of the segments together, A to B, B to C, C to D, D to E, E to F. So let's define each of those. So we calculated A to be 914 joules. Our given values are in kilojoules, so we're going to go ahead and just convert it. Divide by 1,000, so we get 0.914 kilojoules. B to C is our fusion value. That was a given, 6.01. C to D we calculated to be 7,520, or 7.520 kilojoules. D to E is our vaporization. That's 40.67. Notice how much bigger that is. So I mentioned it at the beginning, but going from a solid to a liquid, those are very similar. They're molecules that are close together, pretty small, small movements. When you go from a liquid to a gas, you're spreading your molecules out, you're changing the motion a ton, and so it takes a lot more heat to do that. And then our last segment, E to F, that's what we just calculated. So when we add that all together, the heat to take 1 mole of ice from negative 25 degrees Celsius all the way to steam at 125 degrees Celsius is 55.9 kilojoules per mole. And again, that is for 1 mole. If we were going to do this calculation with something other than a mole, we again would have to take that into consideration when we're using our known values. So I want you guys to try this now. A couple of things to remember. Calculate Q for 50 to 0. Use the negative delta H of fusion because we're cooling down on this one. Calculate Q for 0 to 30 and add them all together. Okay, so we have 100 grams of water in this, not 1 mole. So go ahead and try it. I'm going to give you the answer right here so that you can check your work. Negative 60.4 kilojoules. Good luck.